Hi, this is Rocket. Today we're going to look at the actual Elmo paper, which is called Deep Contextualized Word Representations. I'll put this paper link onto my video description. Now let's get started. Let's first take a look at the abstract. It mentioned that the word vectors are learned through bidirectional language model, which is pre-trained on a large text corpus. It also says the model performs pretty well on 6 challenging NLP problems, which are the downstream tasks using Elmo embedding. Next, we can go to the introduction part. At the beginning, the paper talks about some of the challenges of learning high-quality word representations. The first challenge is that we need to capture complex characteristics of word, mainly the syntactic and the semantic information. Secondly, we also need to make sure our word representations can vary based on the contextual information. Recall the bank example I gave in the last presentation. Next, the paper mentioned they have a new model, and it uses LSTM, and they just call it Elmo. The paper also mentioned the Elmo representations are deep, and they use bidirectional language model. In this case, it's a bidirectional LSTM. And they stack multiple LSTMs so that it can improve the performance over just using top LSTM layer. By stack, it just means they put 2 bidirectional LSTM layers on top of each other. And the paper also shows that the higher level LSTM layer captures semantic information, while the lower states capture the syntactic information. Recall my presentation last time. All this is saying is they stack 2 bidirectional LSTM layers like this. This is top, this is bottom. And they're saying the lower level bidirectional LSTM captures syntactic information, and the higher level LSTM captures semantic information. Going back, here it says they did extensive experiments, and they show that it's improved the state of art, including up to 20% of relative error reductions, which indicates Elmo performs very well in the downstream tasks. Next is the related work section. At the beginning, the paper talks about the traditional word-to-vec method. It mentioned that it does have ability to capture syntactic and semantic information of words, but it is context independent, which means the word representations will not change based on the context. You can skip some of other related work and goes to here. It mentions in this paper it takes full advantage of some of the dataset, which contains about 30 million sentences. This is a dataset Elmo uses to pre-train its bidirectional LSTM layer. You can just get an idea of the sizes of the data that Elmo uses. Notice the paper also puts a code link here. In the next video, we will go through this. You can skip some of the other related work here and goes to here. Here it mentions after pre-training the bidirectional LSTM layer, they fix the weights and add a downstream task to further train the model. And this can leverage the rich and universal word representations. In the next section, the paper talks more details about Elmo. In section 3.1, the paper talks about the stacked bidirectional LSTM layer and the character encoding layer. In section 3.2, it talks about the Elmo layer. In section 3.4, the paper gives some details about how they train the Elmo embedding. And in section 3.3, the paper talks about how they integrate Elmo embedding into downstream tasks. Now let's go to section 3.1. First, the paper gives a background of forward language model. That is, we use tokens from T1 to Tk-1 to predict the token at Tk. Writing this down in mathematical form, that is, every time we use tokens from T1 to Tk-1 to predict Tk, and we multiply these probabilities together, that is equal to the probability of the whole sequence from T1 to Tn. However, in reality, it will be really hard to compute the probability of a sequence in this way, because it's really hard to compute the probability of every component on the right-hand side. That's why this paper is saying we can compute a context-independent word representations using character encoding. This is called base word representations, and then we pass this base representations to LSTM layer. And for each token, let's say token K, this LSTM layer would have a hidden representation for it. And we can use this hidden representation to predict the next word. Also notice, here it uses L layers of LSTM, which means for every token, it would have L hidden representations, and they only use the top hidden representation to predict the next word. This is different from Elmo, because Elmo uses the information of every layer, and this difference will be shown in the later part of the paper. That's all about the forward language model and how we compute it using LSTM. The backward language model is mainly the same thing, but we just compute it in a reverse way. We're giving token from tk plus 1 to tn, and we want to predict the token at tk. We can achieve this using the backward path of LSTM. In terms of notation, the hidden representation of token k using backward path of LSTM has a left arrow here, while the hidden representation of token k computed using the forward path of LSTM has a right arrow here. And for the bidirectional language model, we just combine the forward and backward language model. The actual math expression is not important here. But what we do need to know is that for every token k, we would have a hidden representation computed from the forward path of LSTM, and we have another hidden representation computed from the backward path of LSTM. That's all about section 3.1. It gives some background of the forward and the backward language model, and it also shows us how LSTM can be involved in the forward and backward language model. It also mentions about computing character embedding using convolution layer, but it doesn't give too much details about it. Please refer back to my previous presentation if you're interested. Section 3.2 talks about the Elmo layer, which is a combination of the intermediate layer representations in the bidirectional language model. If we have L-layer bidirectional language model, then for every token, we would have in total of 2L plus 1 representations. The reason for the 2L is because for every bidirectional language model, we have a forward representation of a token and a backward representation of a token. If you look at the math formula here, RK stands for the representation of token K. It is a combination of the base embedding, which we got from the character encoding layer, and the forward and backward representation computed from L layers of bidirectional language model. Next, the paper changes the notation a little bit. For J's layer, they combine the forward and backward hidden representation of token K together and remove the arrow sign. Just write it as H, K, J. This is for J in the range of 1 to L, and when J is equal to 0, H, K, J is just equal to the base embedding from the character encoding layer. And for the Elmo embedding of token K, it's just the weighted sum of all the H, K, J, where the weights S are softmax normalized, which means the summation of Sj from J equal to 0 to J equal to L is equal to 1. We also have a parameter gamma here, which can scale the entire Elmo vector. In the next section 3.3, the paper talks about how we use Elmo embedding in downstream tasks. The paper mentions again, after finishing the training of bidirectional LSTM, they would freeze all the weights. And then they would concatenate Elmo embedding of token K with its base embedding. and pass it to the downstream tasks. Personally, I don't think this step is necessary since Elmo embedding already contains the base embedding inside it. So we can pass down the Elmo embedding into the downstream tasks directly. At the bottom of this section, the paper also mentioned it would be beneficial to add a dropout to Elmo and also add L2 regularization so that the Elmo embedding would have better performance. In the next section 3.4, the paper gives some hyperparameters while they're training the Elmo embedding. For instance, the paper mentions they use 2 layers of bidirectional LSTM, and the sequence length is 4096, and the hidden dimension size is 512. We can skip the rest of the information since they're not quite relevant to our model, and we can go to the next section, evaluation. In this section, it shows the performance of Elmo on 6 NLP tasks. The paper mentioned that simply adding Elmo embedding will achieve a new state-of-the-art result, and with the error rate reduction from 6 to 20% compared with the previous state-of-the-art result. Table 1 down below lists all the 6 tasks and the previous state-of-the-art result, and the result after adding Elmo embedding. We can see there are improvements on all those tasks. The rest part of this section just talks about those 6 tasks and the previous state-of-the-art result. So we can skip them and goes to the next section, analysis. In this section, the paper provides some ablation analysis to validate some of the Elmo embedding performance, and we can briefly mention some of the results here. The first experiment that the paper does is described on section 5.1. It compares the performance on some of the downstream tasks using the word representations from different layers. Table 2 shows the result of this analysis. The baseline means we use the word representations only from the character encoding layer. Last only means we use the word representations only from the last layer of bidirectional LSTM. And all layers means we use the word representations from both the character encoding layer and all the bidirectional LSTM layers. We can easily see that all layers have the best performance. And also notice inside the all layer, the paper also tries different regularization parameter lambda. We can see that when lambda is equal to 0.001, it has better performance. That's all about section 5.1. In section 5.2, the paper talks about where to include Elmo. This is saying for some downstream tasks like squad, we have question on the answer, so 2 sequences in total. So this paper just compares the model performance while adding Elmo embedding into the input sequence and also adding Elmo embedding to the output sequence. The result can be seen in the table 3 here. You can see for most of the tasks, adding Elmo embedding in the input and output sequence would achieve a better result. That's all about section 5.2. In the next section, 5.3, the paper does more analysis about the bidirectional language model. Recall that at the beginning of the paper, it mentioned that the first bidirectional LSTM layer learns syntactic information, while the second bidirectional LSTM layer learns semantic information. And the result shown in Table 5 and 6 just proves this statement. Table 5 shows the result for WSD task. WSD represents word sense disambiguation. So in order to do this task well, the model needs to have some semantic understanding of the sentence. As you can see in this table, the second layer of bidirectional LSTM has better performance. So this just indicates the second layer of bidirectional LSTM captures more semantic information. Similarly, in Table 6, it shows the result of part-of-speech tagging task. Part-of-speech tagging task require the model to capture more syntactic information. As you can see, the first layer of bidirectional LSTM has better performance than the second layer, so it captures more syntactic information. That's all about section 5.3. In the next section, 5.4, it talks about the sample efficiency. The word sample efficiency might be vague. You can just look at the result in figure 1. In figure 1, the x-axis represents the amount of training sample we're using, and the y-axis just indicates the model performance. If we look at this SRL task, the model performance using 1% of training dataset with Elmo is similar to the performance of using 10% of dataset without Elmo. This indicates that with less dataset using Elmo, we can achieve same or even better results than that without Elmo. Finally, is the conclusion section. So in this paper, we talk about Elmo, which includes contextual information into the word representation, and it does achieve better results in downstream tasks. That's all about the paper walkthrough of Elmo. Hope you like this video. In the next video, we're going to look at the source code of Elmo. See you next time.